Alright, so it was brought to my attention that I did this entire video with no sound. So I'm going to run through it again and try to clean things up with sound. Alright, this is 3.1 functions. Alright, my math people. Alright, so before we can talk about a function, we must define a relation because that is a term that's embedded inside the definition of a function. Alright. Now, a relation is a correspondence between two sets. All right, a relation is a correspondence between two sets. So here we have a set state, and here we have the number of representatives for each state. So all you do is look at the relationship between the sets. Alaska has 7 representatives. Arizona has 8 representatives, and you see there's a correspondence between those two sets. So that is a relation. Now a function is a relation with no repeating input values. No repeating input values. That's what a function is. All right, so if we take the definition of of relation and put it inside this definition for function, we can say that a function is a correspondence between two sets with no repeating input values. All right, so let's move on to the next slide. It says determine if the following relation is a function. Up here, at the very top of the screen there, it has the whole mathematical layout function definition. I gave you a layman's term definition on the previous slide. You can read through this mathematical definition. All right, so first thing first, you look at this, you want to determine whether or not this is a function or not. This relation is a function. All right. You look at the input. The input happens on the left-hand side. The output happens on the right-hand side. So the input is the level of education. Output is unemployment rate. So if you input that you ain't gonna graduate high school, your employment rate is going to be higher than everyone else. All right, so you see none of those inputs repeat. So this is a function. All right. Let's move on to the next. You have, first thing I want to ask you, what is the input for this example? If you said calories, it's because you paying attention. That's right. If you said fat, we got problems. Remember, input on the left, output on the right. Okay? So we have our inputs. Let's look at these inputs. Do any of these repeat? We got Wendy's. Oh, we going through all of these fast food joints. Sandwiches. Oh, we got the Wendy's single, the Wendy's Big Bacon Classic, the Burger King Whopper, the Burger King Chicken Sandwich, McDonald's Big Mac, McDonald's McChicken. That Big Mac got all kinds of fat up in it. Lord. All right, but none of those repeat. So therefore, this is a function. All right. Notice I didn't look at the output at all to determine, ask if it repeated. I don't care if the output repeats. To determine if a relation is a function, you have to say that the inputs do not repeat. All right, move to the next. All right, this next example, we look at those inputs real quick. By now you on it, you saying inputs are my carrots. They're on the left. And the price is on the right. That's my output. Let's look at these carrots. I go down, 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 down. Whoa, I got double arrows coming from 0.86. That's because 0.86 is repeating. And if you have an input that's repeating, you have not a function. It is a relation, but it is not a function because this 0.86 happens twice. The output can repeat all day long. Every output value could be the exact same. You can have X and Y, and we have 3, 5, 9. And for y, we have 2. And we can have all of those inputs going to 2. And that's the only output is 2. None of those inputs repeated. Therefore, that would be a function. Roll with me. All right. Let's keep going. All right. This is another setup way that you can identify whether or not a relation is a function. Remember, all right, ordered pairs. When we're looking at ordered pairs, we know that x and y is an ordered pair. The x value would be the input. The y would be the output. The input is associated with the domain. The output is associated with the range. All right. The range is the image of the domain, and the domain is the set of all real numbers such that a function is defined. All right, so we're going to go here. We're not changing our approach. We're checking all these input values first to see if anything. All right, I'm going straight to the inputs. Whoa, I got a double on the 2. Since I have a double on the 2, you already called it, not a function. We're not wasting time here, people. Look at these inputs. No repeat on the input, so we have a function. All right, we're going to write function right beside that. And up under the problem said identify the domain if it is a function. So I'm going to put capital D for domain, and I'm going to put it in set notation and write all of the input values. All of the input values. And for the range, I'm going to put a capital R right there, and I'm going to write all of the output values. Do the same thing for the bottom. We're running through, we're checking. Oh, double tap on the 4. Stop, hold your brakes. That's not a function. And the game. Next. All right, we're going to this function machine, so-called. It's saying, basically all it's saying is you need to be able to identify what your input is. You're inputting inside of that parenthesis. This f right here is simply the function name. The name of that function is f. The function name. In part B, the name of that function is uppercase f. In part C, the name of that function is lowercase g. That's all that is saying. So it's saying input x into lowercase f. All right. I don't know what 1.234x squared is. So I'm going to create a quick other example. I'm going to put in input value of 4. And it says input that value of 4 into the function f for lowercase f. And wherever I see an x, I'm going to square it. And that gives me 16. Boom. It's that simple, people. It's that simple. All right, what if I said input 4 into the lowercase g? Do we run back to part A and try to plug it in there? No. We're going to go down to part C, identify the function g, and wherever I see an x, I'm going to put 4, and my solution, g of 4 equals 2. Thank you. And it's the same concept for this slide. All right? I don't know what happened to cause this slide to start missing components, but it did, okay? And it's not my fault. It was there until we went over to Apple. I'm just saying. But that's another argument. All right. Hashtag Team Android. But anyways, we have part A, f of 3. It says go to the function f. All right. The function f is negative 3x plus 2x. And wherever I see an x, I'm going to put a 3. All right. And notice I left off a very important negative sign at the very front there. So we have, this is negative 27 plus 6 is negative 21, part A. Part B is simply saying take the original function and f of 3 and add them together. That's all it's saying to do. So we're going to take the original function, negative 3x squared plus 2x plus f of 3, which we just calculated. It's done. Done, people. It's done. All right, part C says multiply 3 and the original function. So I'm going to take the 3 and I'm going to toss the original function in parentheses and just distribute the 3. Straight like that. Oh, let me get a quick delete right there. Thank you. 6x. All right. And we're blazing through because we have a lot to cover and we don't want to waste our time. All right. Again, identify the input. The input now is negative x. I'm going to go to the original function, and wherever I see an x, I'm going to input negative x. So that gives me negative 3x squared minus 2x. Now a question would come up, why is it negative 3x squared? I thought you said that a negative times a negative is a positive. Oh, you got to do that squared exponent first. So that is negative x times negative x, which makes that portion a positive, then times negative 3, which makes it back to negative 3x. You're welcome. Part E, negative f of x. All right. Now you want to go ahead and negate the entire original function. Negating the entire original function, you have negative 3x squared. Negated would be positive 3x squared. Positive 2x negated would be negative 2x. All right, we fast forwarding through this. All right, let's go ahead and toss in this portion right here, part F. We have part F is f of 3x. Now this is the part that throws a lot of people off at times, because you have this number attached to the variable and it's the input, but it's the same thing. What throws people off is they do not square that number. They only square the variable whenever they plugging this stuff in. Whenever they're plugging these things in. All right, so we have negative 3 times, all right, now we have 3 squared right there, so that's 9x squared plus 6x equals negative 27x squared plus 6x. All right, and we're getting close to the end of this extremely long example, so but we're going to need to clear off the screen. All right, so allow me to clear the screen. I hope you already took care of everything on the left side. And now when you plug it in, like we're plugging in a binomial, nothing changes. You still plug in like you've been doing. Plug it in, plug it in. All right. That commercial might have been before y'all time, but anyways, I still roll with it. All right. Everywhere I see an x in the original function, I replace it with the input x plus 3. All right. Now, what throws people off is when they put in that x plus 3, they start distributing that exponent. No. You got to write that guy twice. That's what that exponent told you to do. All right. Now that you've written it out twice, you have negative 3 times. All right. If you want to go ahead and do your box or whatever it is that you do to distribute those binomials, you're going to go ahead and distribute those, and you get x squared plus 6x plus 9 plus 2x plus 6 E equals negative 3x squared minus 18x minus 27. Hey, my country swing came out of it just then, million strong, baby. All right, my bad. Minus 3x squared minus 18x minus 27 plus 2x plus 6 equals, we have negative 3x squared minus 16x. We combine like terms. Those like terms, negative 18x and positive 2x, minus 21. That guy is done. All right. Now, this last gal right here, part H, that right there is way scarier than what it is. All right. Let's just clear off that piece right there. But just go back and make sure you can do part G. But part H, it's going to need a little space, so I need to get rid of all of this. All right. All right. So here we go. We have f of x plus h. That input right there. Part H, before I start the example, this has its own name. This is called the difference quotient. The difference quotient. And in all honesty, all the difference quotient is the slope. But it won't make sense right now, right away. But in the future, hey, you're like, oh, it was just a slope. But it's a slope at particular locations, all right? All right, so let's go ahead and dive into this. F of x plus h minus f of x over h is. All right, so first thing first, I need f of x plus h. All right, f of x plus h. I'm going to go to my original function, plug in x plus h squared plus 2 times x plus h. All right. We have negative 3 times x plus h times x plus h, thank you, plus 2x plus 2h equals negative 3. I'd go through your whole distribution and you'll get x squared plus 2xh plus h squared plus 2x plus 2h equals negative 3x squared minus 6xh minus 3h squared plus 2x plus 2h. All right. Now here's the thing. You have f of x plus h. You've calculated it. You have f of x. It was given. Just combine the stuff and put it all over h. What do you mean by that, drummer? Here we go. You have negative 3x squared minus 6xh minus 3h squared plus 2x plus 2h. And then the problem says minus, it says minus negative 3x squared plus 2x. All over that whole thing, all over h. All right, that's it. And simplify. All you got to do is simplify now. So we have negative 3x squared minus negative 3x squared. Anytime you take something away from itself, what happens to it? It goes to 0. Then you have positive 2x minus positive 2x. Again, that part goes to 0. So I did that like that to show you when you're subtracting out f of x, it's going to cancel every time if you do it properly. And what remains is everything that contains an h. you're left with negative 6xh minus 3h squared plus 2h. If you have something in the numerator that does not have an h in it, it's because you made an error somewhere. And once you've done that, you can go through and reduce your h's in all your locations. And your final answer is negative 6x minus 3h plus 2. You're welcome. All right. Take your time on this. Go back, play it a few times because it takes a little practice. Oh my goodness. Why would you do this to me? All right, we got an equal sign here. We have a... Oh my goodness. Stop playing with me like this. We got a plus sign here. Let's say we have a plus sign here, a minus sign here, equal sign here, a minus sign there, parenthesis there, equal sign there, minus sign there. I don't know. It was all there once upon a time in the good life when we just made a problem. But it wants us to find the domain of each of the following functions. All right, when calculating for the domain, I like to point out what I like to call possible domain restrictions. Possible domain restrictions. All right. If you see a rational function, meaning you have a function over a function, p of x over q of x, that's a function on top of another function. To calculate the domain, you take the, I didn't mean to put an equal sign. To calculate the domain, you will take the denominator and set it not equal to 0 and solve for the variable. That's the first one. All right, then we have, if you have a radical function, an even root radical function, to be more precise, and whatever your expression is. To calculate the domain, you take your expression and you set it not equal to 0 and solve for x. And then if you have negative exponents, all right, these things are red flags, right? And let me just put this note right here. I know I said even root radical, but I want you to just remember that n has to be even in these radicals. All right, negative exponents, you treat those quite similar to the rational function. Anytime you see a variable in the denominator, set that denominator not equal to 0 and get to solving. All right, so we're calculating domains. Part A, this guy right here, it looks just like a rational function. It is a rational function. And since it is a rational function, what we're going to do to find the domain is take the denominator, set it not equal to 0, and solve. So we have x plus 3 times x minus 1 not equal to 0. X cannot equal negative 3 or positive 1. So the domain is all real numbers except for negative 3 or positive 1. All right. That's part A. Part B. With part B, do we see any rational function in part B? No. Do we see a radical in part B? No. Do we see any negative exponents? No. Everything that you can read about part B goes straight across. There's no function over a function. There's no fractional exponents. There's no negative. There isn't any negative exponents. And since you don't see any of these things, all right, that's a quick highlight. Real domain, all real numbers. The double line with the R represents all real numbers. Now, part C, check that guy out. Part C, off bat, you see square root of some expression. Square root, square is even. That's letting you know the n is even. So to find that domain, you got to take that expression that's up under that square root and set it greater. Oh, I'm so glad I went through this example. I wrote not equal to 0. Forgive me. That should say greater than or equal to 0. So you take that expression and you set it greater than or equal to 0 and solve for your variable. So we have negative 2x greater than or equal to negative 3 because we subtracted 3 from each side. Divide each side by negative 2. Don't forget when you divide across an inequality that you have to flip your inequality symbol. So your domain is all real numbers that are less than or equal to 3/2. And that's the rundown for finding domains. All right, let's move on to the next. Operations on functions, it's straightforward, okay? You have an f and g function, just add two functions together. You have f and g function, subtract that. The only thing with the subtraction of two functions, make sure you toss that function that follows that negative sign, the whole function in parentheses, so you distribute that negative. Multiplying functions, you treat it just like you do any kind of distribution setup, where you multiply binomials, trinomials, binomial, and trinomial, or any kind of polynomial, whatever you multiplying. I treat it just like a distribution. In quotient, put the function over a function. Lord, I don't know why this just keeps doing this to me, making my life so difficult. All right. But anyways, this is the last example. You have f, it says f and g, add them together. So you take those two functions, 2x squared plus 3 plus g of x, which is 4x, plus 4x cubed minus 1. Combine like terms, simplify, write in order of descending power. 4x cubed plus 2x squared plus 2 in there. Subtracting, you have function f, 2x squared plus 3 minus. Notice the second function, I tossed it into parentheses, equals negative 4x cubed. Then we have negative times a negative 1, that's positive 1 plus 3. And that's plus 2x squared plus 4. So, y'all fact checked. Make sure I didn't make an error. I am human. Okay? And part G, we said multiply those two together. You have 2x squared plus 3 times 4x cubed minus 1. When you multiply those together, you come out with 8x to the 5th plus 12x cubed minus 2x squared minus 3. And finally, when you have that rational function set up, the quotient portion, you take those functions and put them over each other, just like the problem tells you to do. And if it can be simplified, you would simplify. But in this case, this cannot be simplified. And that is your time for this section on 3.1 functions. All right, math people.